So yesterday we looked at parametric equations. Today we're looking at another coordinate system, one that will very much come up in your Calc 3 classes or in physics and engineering. And it's the basis for the other 3D models that we use. So we have our Cartesian coordinates, we have polar coordinates, which is also generally, well, polar is 2 dimensions. Cartesian can go to 3, or we can have x, y, and z. If we extend polar, we could have cylindrical coordinates or spherical coordinates. And those are really nice anytime you have that type of symmetry. So you'll find that you'll learn to integrate in terms of those other coordinate systems. And sometimes it's very much beneficial to choose a different coordinate system depending on the problem you're looking at. But all that's based on polar coordinates. And good old Isaac Newton came up with this because, you know, he had nothing better to do and he was a brilliant man. So the first thing I want to ask you guys is, what does this remind you of? Can you think of anything that looks like what I'm showing you here, the polar coordinate system? And I can't see any of you currently, so you have to just blurt it out. Nothing coming to mind? How about this? And I know at some point you've seen a film where they've had a plane and they've been talking about on their radar, right? And radar is nothing more than a polar coordinate system. And the pole is what we call the origin in the polar coordinate system. And that would just be the origin of the radar, right? So the plane, more than likely, or the the tower. And then you would be given the distance from that object, that's your radius. And you'd also be given an angle. This is usually going to be in radians. So any kind of coordinate in the polar coordinate system is represented by r and theta. R is the radius, theta is the angle. And we always measure our angles from the positive x axis. And then we go counterclockwise. So first, let's go ahead and learn how to plot some coordinates. And then the rest of class will be learning the relationship between polar and rectangular, or polar and Cartesian, for coordinates. Then for converting functions, and then finally doing calculus with polar coordinates. Excuse me. So this first coordinate here says a radius of 2. Well, here's the first circle, the second circle. So this is radius 2. So I have to be on this circle somewhere. Right? And then an angle of pi over 6. So I see right here is pi over 6. So I go right there and I put a dot. Doesn't want to erase. Go away. All right. So that is point A. Now let's try another one. We've got radius 3. So now we're on this circle. And it has an angle of negative 2 pi over 3. So instead, let's find the positive angle. And let's add 2 pi to that. So 2 pi is a full circle. That'll give me the positive angle that represents that angle. And so this is what? 2 pi times 1 minus a third, or 4 pi over 3. So if I start at 0 and I go counterclockwise, I'm looking for 4 pi over 3. That's down here. And I need to be at a radius of 3. So it looks like right there. The other way you could have thought about it, right, was this gets you to 2 pi over 3. Well, I have to go that same distance, but in the negative direction. So that would get me there. Right, that's negative 2 pi over 3. All right. What about this next one? It says a radius of negative 2. Well, we only have positive radii, so that's strange. So let's take care of the angle first. Let's start there. So first, let's locate 7 pi over 6. So it appears it's right here. Now, radius of 2 would be along this circle. And 7 pi over 6, right, is down there. So we're thinking there's our point. But because the radius is negative, that means, you know what? I need you to go back 180 degrees. So if we go back 180, it's actually going to put us back at that point A that we used earlier. So this is both A and C. So this is interesting because this means there's more than one way to represent a point in polar coordinates. Right, that same position I represented by 2 and pi over 6 and negative 2 and 7 pi over 6. All right. Negative 1, negative 8 pi over 3. So the negative radius means once we figure out where the angle is, we're going to go back 180. We need to figure out where's 8 pi over 3. So is 2 pi enough to subtract that from? I think that's still going to give us a negative, right? Because 2 pi is really, well, let's make it over 3. That would be 6 pi over 3. So that's still going to give us a negative angle. So we need to go another 360 and add 4 pi to this thing. So now if we get a common denominator, that is going to be, actually we could pull out a 4 pi. And we'd have that, right? So it looks like 4 pi over 3 again. So that's down here. But because the radius is -1, we need to go 180 degrees. So we think our point's here. We go back 180. And that puts us at pi over 3. So our point is actually right there.
I have a quick question.
Yeah, go ahead.
I was in the bathroom for D. Why did you use 4 pi instead of 2 pi to subtract the 8 pi over 3?
Because 2 pi is just too small in order to get a positive angle.
Oh, okay. That makes sense. So you just make it as big as it, like in order of 2 pi.
Yeah,
to
numbers
make it.
of 2 pi. Yep.
All right, awesome. Thank you.
Okay. So now we've got this last one here, which is -17 pi over 12. Again, I think we're going to need 4 pi for that. Let's see. Actually, no. Excuse me. 2 pi should be enough. So multiply this by 12 to get a common denominator. And that's what, 7 pi over 12. So let's locate 7 pi over 12. It's right here. Notice we have a negative radius. So it's radius 4. So 1, 2, 3, 4. So we think it's there, but we need to go 180 degrees, which would actually put us down here. Okay. So those are some ways to plot points in the polar coordinate system. Let's go ahead and now extend our understanding to converting coordinates from one to the other. And we need to know these 4 equations. But these, if you have taken certain classes or just remember some of Pythagorean's identity, should be very familiar to you. Right, the first one here just says that x squared plus y squared has to equal r squared. So that's our Pythagorean identity. And then the angle theta, right, if we take the tangent of the angle, that's equal to, we don't need these here, y over x, right? And therefore, if you solve for theta, you get this equation. Excuse me. The other two are related to trig as well. If I take the sine of the angle, for instance, that is y divided by r. And so if I just multiply the r to the other side, I get that equation. And the same thing for the x. So all these equations are something that you've come across before, just maybe never, put the two together to understand that we actually could change from one coordinate system to another. So let's go ahead and start converting. I'm going to leave this one and I guess this one for you. And I'll do the other two. So convert 1 square root of 3 to polar. So that means this is an x and a y because it's in Cartesian. And if I have x and y and I want to get to r and theta, I need these two equations. So r equals the square root of x squared plus y squared. So square root of 3 squared is going to be 3 plus 1 is 4. And we all know that's 2. Now, technically, it's plus or minus 2, right? So we have to determine which one it is. Theta is the arc tangent of y over x. Somebody tell me what that is?
I got 1.047.
And that's radians.
Yeah.
Okay. Can somebody give me an angle as well? In degrees, please.
And that's 60 degrees.
Exactly 60?
Yep.
Okay. So yeah, if you would have taken this 1.047 divided by pi, what do you get?
0.3.
So that would be approximately pi over 3. Or no, sorry. You're getting 0.333. So yeah, it should be pi over 3, sorry. Right, so if you want to leave it in radians, that's pi over 3. All right, so our angle, or sorry, our coordinate is 2 pi over 3, we believe. Let's check it. So where does 1 root 3 fall in the Cartesian plane? Well, that'd be 1 and then root 3. And so it'd be up here somewhere. Now, does that point match the angle pi over 3? And yes, it does. So then the radius is positive, and that's okay. So you can check to make sure that they're in the correct quadrant, and that'll tell you if your angle and radius are correct. So that's converting from Cartesian to polar. It's literally just a matter of plugging in the numbers. Same thing for polar to Cartesian. So here I want to go and use the x equal r cosine theta and the other equation of r sine theta. So x equals, and remember this is r and theta here. So this is 2 cosine 2 pi over 3. Y is equal to 2 sine 2 pi over 3. So I think this is -1/2 and 3 over 2. So your coordinate system would be -1. Why are we selecting everything? -1 √3. Again, let's check that. So 2 pi over 3, what coordinate, I'm sorry, what quadrant does that occur in? So we said pi over 3 was here, right? So 2 pi over 3 is over here. So that's 2 pi over 3. And a radius of 2. Does that match up with an x coordinate of a -1 and a √3? So my picture's not going to be perfect. That's almost a 45-degree angle that I drew there. But it does match up with this coordinate, which is in the second quadrant, right? Does that make sense?
Yeah.
Oh, I'm sorry, I meant for you guys to do that one. Oh well, you'll do that one. All right, so those not real tough. Just using those two equations and plugging in the numbers. The next task is to now take those same equations and manipulate them such that we can change polar equations into Cartesian equations. Now, the whole reason the polar coordinate system was created in the first place is basically to represent circles. Right? Circles are really nice to write in polar form. Other functions, not so much, as we'll see as we go along. But you can represent all of them in polar coordinates. All right, so this first one just says r equals 5. So what are we thinking to do here to convert this to Cartesian? Any ideas? Remember, we've got these equations up here to use.
You can plug in the 5 in for R
In for what
for
part?
both X and Y equation and the X and Y equation.
We could, but then we don't have an angle theta, right?
Mhm.
And we're trying to get away from polar and just get to Cartesian.
Could you use the equation that's like r squared equals x squared plus y squared?
So yeah, we could do that. R squared is equal to x squared plus y squared. And in our case, r is 5. So we get the equation 25 equals x squared plus y squared. That is a circle centered at the origin with a radius of 5. So, as I said, circle's really nice to write in polar, right? Just r equals 5 could be a circle. What about this next one down here? R cosine theta equals 1. So this one, go ahead. So yeah, x is equal to r cosine theta, right?
Mhm.
So this is literally just x equal 1. So it looks strange, but in polar, that's the equation of a line. Right. Trying to think which one of these to do for you. I think maybe I'll go ahead and do C. Excuse me. I'll let you guys do D and E. Excuse me. So again, I'm using that combination of four equations above. So here, remember we have x equal r cosine and y equal r sine. Now we can't say that this is x and this, or sorry, this is y and this is x because these numbers are different. Okay, so we can't say r is that number. And in general with these, you won't just pick r to be a value anyway, you'll leave it as a variable. The other thing we have to realize is notice this one starts off with this p of theta, which looks strange, but it's nothing more than r. So if you see some function of theta, it just means r. So I'm going to solve these two equations here for cosine and sine respectively. I'm going to replace the left-hand side with r, and then I'm going to replace the denominators. Right, instead of sine, I'm going to plug in y over r, and instead of cosine, I'm going to plug in x over r. So if I put those two fractions together, right, because they both have common denominator, then I can flip the entire fraction, and I have that. And that all still equals just r. Which means I can divide through by r on both sides. They'll disappear. I have just this. Right, so all I did was Divide by R, divide by R. And I believe I've showed you this trick before, but I could take this entire denominator here and swap it with the value on the right-hand side. And if you don't like that, then you can go ahead and do your, you can do cross multiplication or do both steps, but it works out just the same. We get that. And because we're trying to figure out what this thing is in Cartesian, I'm going to go ahead and solve for y. So this is going to be y equals 1 plus 3x all over 4. Or if you prefer, 1/4 plus 3/4 x. That is an equation of a line who intercepts the y-axis at 1/4 and has a slope of 3/4. So here's where I always thought these things were kind of silly, right? That we're used to that as a line in Cartesian. Now look what it looks like in polar, now that we know what it is. That's a really strange way to represent a line, right? And the last thing I wanted to show you was to, well, not last thing, but before I move on to the next topic, was how do you do this on your calculator? Right, if you want to plot the polar function. So as before, just go to mode. And again, that fourth option down, function, the third option over is POL for polar. You choose that, go to y equals. I'm going to try to put this function in here, see if it likes it. Okay. So that was the result from plugging in that function. So it does in fact give me a line in polar.
Can I see what you plugged in? Because that's just
Um,
not what I.
You mean the equation?
Yeah.
Can you see that okay? So I had 1 divided by 4 sine theta minus 3 cosine theta.
Okay.
Making
Thank
sure
you.
to put a set of parentheses around the denominator.
Thank you.
And then again, remember I said you go to mode. It's the fourth option down, third option over. Okay. So if I asked you to say do that on a test eventually, you could plot it on your calculator and say, hey, this looks like a line. I better get a line when I'm all done changing out polar to Cartesian. So any other questions about converting either coordinates or equations?
Nope.
So I think we can do the derivative here, and then I can set you guys loose. You'll have a couple problems there to solve. Everybody go with that? Little thumbs up is good. Thanks, Hannah. And I'll assume the rest of you think that's a good idea since you didn't say anything. All right. So now we want to do derivatives. We want to do some calculus with this new coordinate system. And the formula here is given to you for the derivative with respect to x. So if instead you're given a polar function and you want to know what is dy dx, then you use this guy. And this always reminded me of, there's a matrix operation you can do that looks very similar to this. So if any of you remember doing matrices or have already taken linear algebra, you may recognize that kind of format. It's not exactly the same thing, but pretty close. So the two things we need for this are, well, actually the only thing we need is dr d theta because we're already given r. So we're replacing all of those. So remember, f of theta really means r. So this is 3 sine theta equals r. We need dr d theta. Well, that's pretty simple. Derivative sine is just cosine. Okay. So we've got r and we've got dr d theta. Therefore, if we want to solve for dy dx, then we just need to start substituting them in. So dr d theta is 3 cosine theta times sine plus r is equal to 3 sine times cosine, all divided by dr d theta again. But this time's going to be times cosine and 3 sine times sine. I'm going to try and simplify this best I can. Darn it. All right, so I've got on top 3 cosine sine plus another 3 sine cosine, right? Doesn't matter that the sines and cosines are flipped. It's all multiplication, so it's the same term. And I have 3 and 3 more, so I have 6 total. Then on the bottom, I've got 3 cosine squared minus 3 sine squared. And if all these trig functions haven't already hinted towards it, now is a great time to grab that trig sheet. So it looks like I could factor out a 3 down here. And then that'll cancel and make that a 2. So do we know what 2 cosine times sine is equal to? You guys gonna make me start calling on people?
Sorry, I was trying to find it. Sine of 2x.
Okay. Right, we used that quite a bit when we were doing our trig integrals earlier on in the semester. And does anybody see cosine squared minus sine squared? Or something close to it?
Would it be -1?
I have it as a cosine of 2x or 2 theta for this instance.
So yeah, that's you would need negative cosine minus sine for it to be -1, Hannah.
Okay.
So that's cosine 2 theta. Well, hey, look at that. What's sine over cosine? That's just tangent. So all that reduces down to tangent of 2 theta. And that's nice because part A says, give me the slope at the given value. Well, but we know dy dx is the slope. Tangent of 3 times the given value. Sorry, 2 times. So we just need the tan of 2 pi over 3. It looks like is it square root of 3, I guess? Yeah, negative root 3 is what I get. And then the last part says find where the function has a horizontal tangent. So I think we're going to want to go back to this form. Horizontal tangents mean, well, we don't have to go back to that, but horizontal tangent means that the slope is what?
Zero.
Right, so I could do tan of 2 theta is 0, or I could solve sine 2 theta is 0. So either one works. Let's do, so inverse tan of 0 is 2 theta, and therefore theta is inverse tan of 0 over 2. So it looks like 0 pi over 2 pi pi over 2 and 2 pi. All right, so arctan of 0 comes out as 0 in your calculator, but we're also thinking about, when's the sine 0? Well, the sine is 0 at 0 and pi, 2 pi, 3 pi, 4 pi, but then you divide all of them by 2. So you get 0 pi over 2 pi, 3 pi over 2, and 2 pi. So one thing I've noticed in the past is the problem says give me all the angles from 0 to 2 pi. And so people will they'll do the 2 theta part, which is this. And because the thing said to 2 pi, they'll stop at 2 pi and they'll forget about these two. But you can't do that because then you have to divide by 2 at the end to get just theta. And notice that my last term here is 2 pi. So you got to be careful as to what you're restricting. Right, these are 2 theta. All right, so the hardest part of this problem, darn it. Hardest part of this problem is probably the simplification because of the trig functions. Right, the derivative isn't hard, and the dr d theta is not hard, and the dy dx is given to you as a function. So you just have to plug in. So nothing special there. So hopefully I didn't do that too quickly, but we have plenty of time for you guys to solve the rest of these problems. But I have a feeling some of them are gonna give you a little bit of trouble, so we'll see. So for changing from polar to rectangular coordinates, I'd like you to do B and D. For changing from polar equations to Cartesian equations, I would like you to do D and E. And then for the derivative, I would like you to do B. So is everyone good to